Hi everyone, welcome back to Dave's Math channel. I'm your host David Tear, and this is my third video in a series on how to be a human calculator. And judging from the popularity of my last video, I take it this one will probably be really popular as well. I think this one you're probably going to be even more amazed than the last one where I mentally computed square roots using Heron's formula. And this one I'm going to mentally compute scientific functions like exponentials, sines, logs, and even pi using what are known as Taylor series or Maclaurin series. And another person who could do this was Richard Feynman. He used to amaze people by doing calculations like this. And so anyway, let's begin. So here, just to start off, I thought I'd show you a picture of kind of an old school scientific calculator. I think believe these first came out in the late 70s. I believe TI came out with the first scientific calculators maybe around 74, 75. That time they were over $100. I think by the 80s they went down to about $30, which is about what they are today. You can still buy them. You can buy these kind of things at any drugstore pretty much, and they're pretty cool. I mean, there's much cooler calculators now that can do graphing or even allow you to program things and stuff. But if you were just taking a like a college STEM course, this would probably be good enough. And I used to use calculators like this all the time. I still do from time to time, but as I'm going to explain this video, you can kind of do some of the same things that these calculators do, and I believe they do use Taylor series to do their calculations. They just use more terms than humans can do, which is why they're able to get up to like 10-digit precision or however many digits are in the calculator display. But anyway, let's just go on. So yeah, I just I have another video in my calculus series. I have a video towards the end of the series on Taylor series and Maclaurin series, which are very important. And I think most people learn these in either first or second year calculus. They're pretty basic, but it's a Taylor's formula. This the formula on top. It's a very I think it's a really beautiful formula. It's a formula that allows if you have what's called an analytic function, which is really just a well-behaved function. Just about every function that people study in the sciences is an example of an analytic function, like trig functions and hyperbolic functions and exponential logarithmic functions and all that. Those are all examples of analytic functions, which means that they're infinitely differentiable uh, over the real or the complex numbers. And if that's the case, then Taylor's theorem says you can evaluate that function in any argument as long as in terms of its Taylor series at some point, as long as you're within the radius of convergence of that point. Which means if you're evaluating f of x, if you're taking the Taylor series about some point A, the radius of convergence is usually we call that r. As long as the absolute value of x minus a is less than r, this series is guaranteed to converge, and it will converge to f of x. That's what Taylor proved back in the 17th century. So very, very useful formula. And below there's 4 examples of common ones: e to the x, sine x, cosine x, and 1 over 1 minus x. Those are just the Maclaurin series. All the Maclaurin series is just a special case of a Taylor series. We're expanding about a equals 0. So you're expanding about the origin, which is usually what we do when we do Taylor series. So anyway, that's what Taylor series are, and you can use them to calculate these analytic functions. And so now I'm just going to jump into some examples. And I've memorized the Taylor series for all these important scientific functions. I'm going to give 4 examples in this video. So the first one, this is probably the easiest example. Let's estimate the square root of e. That's e to the 1/2 or e to the 0.5 if you like. Well, we start with the Maclaurin series for e to the x, which has a very simple form. It's just the sum. I should have probably written down the general Taylor series. You can see it on this slide. E to the x is the sum as k goes from 0 to infinity of x to the k over k factorial. If you want to write down each term, you get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial and so on. That's a pretty easy one to remember. So let's just plug in 0.5 for x and see what we get. So we don't need to keep that many terms. This series converges very quickly. These factorials grow very fast. And we're already starting with a value of x that's less than 1. So not only are the factorials growing fast, which is going to make the denominators grow fast and thus the terms grow small, but we're also taking higher and higher powers of half, of 0.5, which are going to get smaller and smaller. So we can do pretty well with just 4 terms in this case. If you use the 4 terms, which you can calculate pretty well in your head. I don't think these are too hard, probably even for you. So the first 2 terms are just giveaways. 1 plus x, that's always the case when you're doing e to the x. So you have 1 plus 0.5, didn't have to do any arithmetic there. And then the second term is going to be 0.5 squared, which is 0.25. That's not too hard to calculate. If you like, you can use 1/2 squared, which is 1/4, and 1/4 is 0.25. I prefer to work with decimals because in the end, you want to get an answer that's a decimal. So you get 0.25 over 2. 2 factorial is just 2. And then the last term is 0.125. That's 0.5 cubed all over 3 factorial, which is 6. And these terms are already getting pretty small. So let's just stop here. And now we just have to do the divisions on the last 2 terms. 0.25 over 2, that's pretty easy to calculate. This is 0.125. 0.125 over 6. Well, 0.125 just a little bit less than 0.126. 126 is a multiple of 6, and 126 over 6 is 21. So the last term is approximately 0.021. And when you add all these decimals together, you get 1.646. And that is very close to the right answer, which is 1.64821 approximately. So just using 4 terms of the Taylor series, we already got an answer that's almost correct it's correct in 2 decimal places and not that very far off in the 3rd decimal place. Pretty good. We probably could have gotten the 3rd decimal place right if we used a 5th term. But anyway, let's do another example. How about the sine of 15 degrees? This is a harder one because the Taylor series, the Maclaurin series for sine x, which is the second series on the bottom here. This is assuming that x, the argument, is in radians. It's a lot more convenient in math to work with radians than with degrees, but most people, it's easier to think in terms of degrees. Most people, when you're doing trigonometry, you usually are working with degrees. When you're doing geometry, whenever you see a triangle, it's easier to think about how many degrees the angles are than how many radians. So anyway, I guess I went ahead here. So the first thing we have to do is convert the argument from degrees to radians. That's not too hard. If you just remember that pi 180 degrees is pi radians. There's 2 pi radians going around a circle. Just remember the formula for the arc length or the circumference of the circle, 2 pi r. So that 2 pi is just the number of radians around the circle, and it's 360 degrees. So you can remember either 360 degrees over 2 pi or 180 degrees over pi. So the conversion factor from going from degrees to radians is pi over 180. And if you multiply 15 times pi over 180, you get pi over 12. And if you can sort of compute that mentally, or at least I can, pi is approximately 3.14. 3 over 12 is 0.25. 0.12 over 12 is 0.01. So that'll give you 0.26, but then you still have a little bit left over. You have 0.02 over 12, that's 1 over 600, which is about 0.002. So in radians, 15 degrees is approximately 0.262 radians. That's probably the hardest part of this calculation, actually. So now let's just use the Taylor series for sine x. So when we plug in 0.262 radians to that Taylor series, remember that Taylor series was the sum minus 1 to the n times x to the 2n plus 1 over 2n plus 1 quantity factorial all these terms are odd. Sometimes people write this as a sum with n odd. I don't like to write it that way, but anyway. So now let's just use two terms. I mean, we're skipping every other term anyway. This Taylor series looks sort of like the Taylor series for e to the x, except it only involves terms with odd powers. So remember when we did e to the x, we used all the powers up to x cubed. I think here we're doing the same thing, but that only gives us two terms. So the two terms are going to be, the first term is just 0.262, just x if you like, x to the 1 over 1 factorial, which is just x. And then the second term is going to be x cubed over 3 factorial, and x in this case is 0.262. Actually, this is kind of a hard calculation to do in your head. 0.262 cubed. You know, another fancy thing. I told you how I memorized all the squares of all the numbers up to 100 when I was a kid. I also memorized a lot of cubes. I think I memorized all the cubes up to 30 cubed. And I happen to know that 26 cubed is 17,576, which is actually kind of a useful thing to know because there's 26 letters in the English alphabet, which means there's 17,576 combinations of three letters, like HAL or IBM. I don't know if you guys remember the movie 2001. The computer that goes crazy in the movie was named HAL, and each letter at HAL was one letter before IBM. But it was very, very unlikely that that was just a coincidence. Because, and even Arthur C. Clarke, the author, said it wasn't. But you know, what's the chance with 17,576, combinations of three letters that he just happened to pick one that each letter was one letter before IBM. He didn't, but I guess you could make the same argument that the title "Lucy in the Sky with Diamonds" (LSD) initials wasn't accidental, even though John Lennon claimed it was. Anyway, enough of that. But anyway, so 26 cubed is 17,576, which means 0.26 cubed. You have to divide that by 100 cubed, which is a billion. That's going to give you 0.0175, approximately 0.018. And I'm not even worry about this third decimal. I'm just going to call it 0.018. It's easy to work with anyway. 0.018 over 6, that's what we need here. That's going to be 0.003. So we started with x, which was 0.262. Now we're subtracting 0.003, and that gives us 0.259 approximately. And that actually worked. What's amazing to me, I did this in my head. I've never actually done this calculation before. I just did this for the first time when I was making this video. But I did this in my head, and I was right to 3 decimal places. So I'm kind of proud of myself for that. Anyway, let's do another example. How about natural logarithm of 2? This isn't too bad, but you have to use a little trick at the beginning. We could just start with the Taylor series for ln1 plus x. The problem with that is if we did that, we would be using x equals 1. And that's not a good idea because the Taylor series for natural log 1 plus x, let me just go back to it. Oh, they don't even give it on this slide. But anyway, its radius of convergence is 1. So you don't usually want to use an argument that is equal to the radius of convergence because it won't converge very quickly if you do that. But we can use a trick here. We can use a property of logarithms, namely the logarithm of 1 over x is equal to minus the logarithm of x. So in particular, the logarithm of 2 is minus the logarithm of 0.5. And the logarithm of 0.5 is easy to calculate. That one does converge much quickly. We can use the Taylor series of ln 1 minus x to get that. I think I should have put a minus sign here. So the Taylor series of minus log of 1 minus x has a very simple form. It's just a sum n going from 1 to infinity x to the n over n. No factorial here. But as long as x is less than 1, this series will converge pretty quickly. So we're using it here with x equals a half. So remember, natural log of 2 is minus the natural logarithm of 0.5, which is going to be the sum is n goes from 1 to infinity, 0.5 to the n over n. And here, let's take 5 terms, because this one doesn't converge that fast. So we get 0.5 plus 0.25 over 2. Yeah, it's 0.5 squared. Let's just write out the term. So 0.5 cubed over 3 plus 0.5 fourth over 4 plus 0.5 to the fifth over 5. So the first term is just 0.5. Second term is 0.5 squared is 0.25. We're dividing that by 2. That's and then we're taking 0.5 cubed and dividing that by 3, and then 0.5 to the fourth, dividing that by 4, and 0.5 to the fifth, dividing that by 5. So if we do that, you add up all the terms. You just take, 3 decimal places, and you mentally calculate each of these quotients, which is what I did here. You get approximately 0.689. That's okay. I mean, the actual answer is 0.69315, so we sort of messed up in the last 2 decimal places, but we're still within 1%, so we still did okay. I guess we could have just taken a few more terms if we wanted a more accurate estimate. Remember that there's no factorials in this Taylor series, so that's probably why it doesn't converge as fast. You need more terms. I'm gonna do one final example. I'm gonna mentally calculate pi. I think you guys are gonna be pretty amazed by this. I'm gonna use so the way we want to calculate pi, you probably know from trigonometry that pi over 4 is the arctangent of 1. Remember, the arctangent of 1, if you're more used to degrees, the arctangent of 1 is 45 degrees, because 45, 90 right triangle, that's just an isosceles right triangle, has a slope of 45 degrees, and you know that the legs have equal length. So therefore the arctangent of 45 degrees is 1, and 45 degrees converted to radians is pi over 4. So the arctangent of 1, the tangent of pi over 4 is 1, which means the arctangent of 1 is pi over 4. And there is a nice Taylor series for the arctangent. It wasn't on my cheat sheet I showed you at the beginning, but it has a pretty simple form. Kind of similar in a lot of ways to the natural logarithm. So here's what it looks like. The arctangent of x is the sum as n goes from 0 to infinity of minus 1 to the nth power times x to the 2n plus 1 all over 2n plus 1. And if you just write out the first few terms, you get x minus x cubed over 3 plus x to the fifth over 5 minus x to the 7 over 7, and so on. Pretty easy to remember. The pattern is pretty easy to see here. And if you plug in 1 for x, that'll give you a formula for pi over 4. And this is a very well-known formula. As a matter of fact, this is known as Leibniz series. I don't think Leibniz was the first person to discover, though. I think it was actually James Gregory. But I guess Leibniz got credit for it. Maybe sometimes people call this Gregory series now. But anyway, it has this nice simple form. Pi over 4, you plug in an x, 1 for x. You just get 1 minus 1/3 plus 1/5 minus 1/7, and so on. Pretty nice formula. But unfortunately, it converges very, 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 very slowly. I mean, if you wanted to calculate pi to 6 decimal places, you would literally need a 500,000 terms. You need the denominator to go up to 1,000,000, which means you need 500,000 terms, which is completely impractical. There are shortcuts to doing it better, but we want to do better. We clearly want to do better than the Leibniz formula. So how can we do better? Well, there was a guy named Maschen who came up with you can use properties of the arctangent to derive this really amazing formula, I think. It turns out that just using our properties of the arctangent, like the addition formulas and subtraction formulas, you can get this formula, which says pi over 4 is equal to 4 times the arctangent of 1/5 minus the arctangent of 1 over 239. Who would have thought? But this is a true identity, and this identity actually allows us to calculate pi really, really fast. As a matter of fact, this has been used in a lot of computer programs to calculate pi. It's still a very fast formula. I've done it myself a few times. I think I wrote code back in the 80s that computed pi to 2,000 decimal places, which is what actually the first computer that ever calculate pi. This was done in 1946 by ENIAC, and they got it to 2,000 decimal places. I think 2,035 decimal places actually, using Mashin's formula, using this formula on the top of the slide. But you can even do this do this in your head, or at least I can. So here's where I'm going to amaze you guys, I guess with my computation ability. I'm going to use Mashin's formula here to come up with a really, really accurate estimate of pi in my head. And you'll see how I do it. So there's actually two terms in this sum. There's two arctangents. So we have to use it twice. But the second term we don't worry about so much because 1 over 239 is a very small number. It's enough to just use one term. And 1 over 239 is approximately 0.004. I'm going to use 0.004 as an approximation of 1 over 239, and I'm not going to worry about any of the higher order terms. So now we really only have to concentrate on the arctangent of 1/5. And again, 1/5 is a nice argument because it has a nice decimal, 0.2. I think this is one reason computer scientists like this formula, actually, because it has a nice decimal conversion, at least for the first term. So let's do this. So we get 4 times just using the top formula, the Taylor series for the arctangent of x, plugging in x equals 0.5. We get 4 times this sum of n going from 0 to infinity minus 1 to the n times 0.2 to the 2n plus 1 all over 2n plus 1. And then finally we're subtracting 0.004. Well, let's just write out the terms in this sum. And I'm only going to use the first 2 terms because these I mean this is kind of like the sine formula. Remember, I only used the first 2 terms in that. That was mainly because the denominators were growing very fast. They were factorials. Here they're not factorials, but the advantage we have here is that the numerators are powers of 0.2. 0.2 is 1/5. So 0.2 cubed is already really small. It's only 0.008. 0.2 to the 5th is really, really small. So it's probably just enough to use 2 terms here. So that's what I'm doing. So the first term is 0.2. That's pretty obvious. Second term is 0.2 cubed. That's 0.008. That's not too hard to see. 2 cubed is 8. And we're dividing by 1,000 because 0.1 cubed is 0.001. So we get 0.008 over 3. And then finally, I'm putting this 0.004 in the parentheses, but since we're multiplying everything by 4, we have to divide that by 4, so we get 0.001. So now we just, the main thing you have to do is this division, this quotient in the middle. Well, 0.008 over 3, 81 over 3 is 27. So it's approximately 0.0027. And we're subtracting it. And we're using 4 decimal places now, which is why I added another decimal after the 0.001 on the right. So when you do the subtraction, now this is pretty easy. I think you can do this in your head. 0.2, so 2,000 minus 27 minus 10 is 1963. And of course, there's a 0 in front as a decimal. So we have 0.1963 for the, that's our estimate of the quantity in the parentheses, but we're multiplying that by 4. And that gives us 0.7852. This is a pretty easy calculation, at least for me, to do in my head. You can double twice if you like. But we're still not done. That's our estimate of pi over 4. We have to multiply by 4 again. And when you do that, you get 3.1408. Well, I think you guys know pi. Most of you probably know pi to 4 decimal places, 3.1416. Got pretty close, didn't we? We got 3.14, which is what most people, most people usually need for pi, and most of the time. And we did even better. We actually got within about 1 part in 4,000. Just from this mental calculation using Mashin's formula. I think that's pretty amazing. So that's how you can calculate pi in your head. And if you want to impress your friends, maybe you can do this for them. Anyway, that completes my video on how to be a mental calculator. Thank you for watching. Long live math, and I'll see you guys next time. Bye.